Good morning, good afternoon, everybody. Welcome back to lecture number
28?
30, 29.
29, yes.
29. So we're at to 10, 11, 12. The test in week 12 or 13?
13, I think.
Test in week 13
Mm-hmm.
on April 14, okay?
Mm-hmm.
Yes.
Tuesday. We'll discuss the exact time later, but maybe 7 p.m., 7 or 6. You choose. Okay? Any objection on the test date? We can do another round of
No.
schedule. You both were absent as lectures, huh?
Yeah.
It's recorded. So, the project. So, due date is not April 13. This is so what I'm presenting to you today is revision 1 of the project. There will be a final version that will be posted 1 or 2 days. So the final exam, so we have major 2, April 14th, right? We have final exam, May. You see the schedule?
No.
Okay, it's May 13th at 8 a.m. Okay? I don't think it will change.
No.
Okay? So the project is going to be 3 days after. Okay? At what? 11:59. Okay?
Is the final fixed on 13?
Hmm?
The final is fixed now on 13?
Yes.
Oh.
So I'm going to give you 3 days after the final. If you want. But I expect you to do it before.
Mm.
For the presentations, you present online to me, okay?
Mm.
And before you present, you record yourself with me, okay? So just call me at any time, 5 minutes. I'm gonna check your presentation anytime you call me, okay? Okay?
It will be an online call or I record the video and send it to you?
No, online call, live, okay? Because I will ask questions.
Mm.
Anytime before this, you can do the presentation, okay? This to gives you more flexibility, okay? So how many objects do you have?
Which one is object?
Objections.
So you have 2 options, okay? Project 1, DC drive simulation. What are you going to do is, let's go back to the slides. Do you remember last lecture we talked about remember this block diagram? So you're gonna focus with me. You're gonna fill this tape, this block, and this, and this, and this here B is this one will be 0. There will be no friction. And this, and then the load model. So how many blocks you need to fill? 1, 2, 3, 4, and then there is 1, 5. Nothing else. And then you run the simulation and write the report. Let's go to this Simulink model. You're going to load the parameters here, okay? These are the parameters, for example, RA, LA, K times phi. You're going to see it in the project statement. JL, JM, J, K torque, I rated, T rated, those are the parameters. If you go to the Simulink model, if you go to the project statement, you're going to see that we have a speed command we take the speed reference. In the lecture we took it where? To Vt. Because K times omega, this is K flux. K flux, this is the constant, times omega is what? A voltage. You subtract it from the voltage. This is the electrical model. So you're going to have Ra, La, and the numerator you're going to have 1. Here you have the same constant. Here 1 over Sj. There is no +1 for the friction. Get it? So you fill this, you fill this, you fill that, and then you have the T load or T work. The speed command is already in the Simulink file. We start, how many seconds the simulation? 4 or 5, okay? You're gonna start ramping up the speed until 500, then you're gonna drop it until -500. Then you stay. Okay? So these are the parameters. What is required? This is not complete. What's required is Simulink and M file, 2 files, Simulink and M, compile them. Report how many pages? 5 pages, do not exceed 5 pages. It does not have to be IEEE format for the simulation project. Any reports can allow. And 5 slides presentations. You present it to me. The grade distribution is in the report 4. Anything else is 3. You go to the simulation model. It is a little bit more big because those are oscilloscopes, there's some supplemental functions, time, clock, etc. So the stop time is 6 seconds. So you fill up this, you fill up this gain, you fill up this gain. These are the same gains. You fill up that, you fill up this gain. This is omega squared, so we square the speed. And then, what is the, if you go to, what is the model of the speed? It's fan. So it's a constant 0.016 times omega squared. Okay? You either don't put it as a number, identify it as a variable. Okay? Constant times. So this is the K times flux. It is in the unit of voltage times second. Voltage times second times radians per second. It will be what? It will be voltage times radians. So this K flux is a number already given to you. It's here, so you put it. The transfer function, what is J? Inertia. This is the inertia, 1. This is the resistance. This is the L. Okay? Get it? It's easy. Is it easy? So you just need to fill up these. You don't need to build the whole thing. And run the simulation and put the requirements. These are the requirements that the TA is asking: motor speed, torque, current, speed, error, etc.
الحين هذول البوكسز نبيهم كيف تحطوا ارقام ترايل
They figure it out. No, figure it. No, not try and error. It's already given, but you need to figure out what's the proper box. Is it a gain? Is it a transfer function? Is it a sum? It's your job. Now, how many students can work on this project? 2. Any question? For the other project, if you don't want to do the simulation, now for this project, or even 1 student can do the simulation. You don't have to do it. Up to 2. So if you want to do it alone, you can do it alone. For the other project, it's a small paper. There is no simulation. Now you know why the east-west petrol line is important. So it extends from Gate till Yamba. So what I want you to do is write more about this pipeline, why it is important, when it was built, how much did it cost, what company built it, what is the purpose, put maps, size of the pipes, capacity of each pumping station, capacity max, min, etc. What type of liquid is flown? There was a point where it was sending gas, then it became oil, was oil, gas, and then back to oil. I want to talk about the pumping stations. What is a pumping station? What type of machines used for pumping stations? What are the controls typically used? You might not find references for that specific oil pipeline, but you might pumping oil, but you might find for other plants, and maybe you can list types of machine, induction, what's the size, what's the rating, put pictures of those machines. You can use AI. This is the layout of the paper. Rating, physical, control, drive system, operating. Now I will update a better version. This is not the final version. And the 5 presentations. So 5 points for the reports, 5 points for the presentation, because there is no simulation. It has to be IEEE format. How many columns the IEEE format? If you don't know how to find it, if you just type in Google IEEE template, you can download IEEE template, okay? And then you can put your papers. AI is not allowed for writing, okay? It is allowed, you can write your paper and upload it, and it gives you a review of the paper, criticize your paper. It gives you suggestions. This is allowed. What's not allowed is you put the text and then copy it and paste it. It's not allowed. You have to work through the process of looking at the suggestions and put it yourself. The more typos is better for me. The more typos, yes. Okay? I want you to go through the process alone, because what if they ask you to write a report in front of the management without the use of AI, confidential information? So I want you to go through this exercise. I want to see mistakes. The other thing is you can use it as a search engine to find references. You might find references from the 60s, the 70s, maybe in the library. Do your best, okay? If you don't want to do the simulation. Any question about the project? Father? So who's going to do the simulation? Who's going to do the paper? Do whatever you want, okay? Now, if you cannot reach the paper for 5 pages, 4 is also allowed. 4 is okay. With the references, okay? With the references, 4. That's fine. It might be difficult to reach 5. You can have photos, etc. Any question?
الصفحة الأولى cover base صح؟
Yes. No, for the IEEE it's not covered. You have to check how it looks like, part of the exercise. Okay? The CVs, whoever sent me CVs, we need to talk. Okay? I'm not gonna go edit the CVs myself. I need to meet with you online or in person and then go over this. Some students did it. I know 2 or 3 did it. Come visit me or call me on Teams. I'll give you feedback about your CV. Okay? Clear? Now it's time to apply. You have career fair. When is the career fair? There's a career fair.
سمستر
There will be. You are
28 إلى 30.
There will be a career fair. Okay? Okay?
Yeah.
Clear? Fine. So make sure you get your CV polished before the career fair, okay? Sometimes they do interviews in the spot. My favorite company is doing sometimes. They might do. You know what's my favorite. Okay?
So, في كارير فير ثاني؟
Yes, there will be. April 18,
18.
I think so. Or 14. لا يكون نفس يوم الميجر.
28 إلى 30.
No, it was the first day.
28.
خلاص okay, good.
لينكدين حق الجاب شيء.
Yes, there will be.
طلاب ولا للشركات؟
Okay?
لا طلاب. شركات تقديمهم 6 أبريل زي ما تقول.
لو الطلاب ايش نستخدمه؟
بالأسلوب.
Okay? I'm not gonna go and edit the CVs. You have to call me, okay? You have to call me. All the CVs that I saw are bad.
تحدي صح؟
Yes, yours is the first one. Because you remember, you had what? Gray, صح?
ايش؟
كان gray on it, صح?
لا اسود.
طب حتى انت مشيت حقي
لا ما شفت.
بس شوف حقي
كان فاضي في فراغات. ها؟
كان راجع
The news.
نرسل لك تيمز ولا نجي مكتب ولا؟
It's up to you. Teams is more efficient because sometimes I might not be in the office. But if I'm in the office, feel free to come.
بيرسون احلى
Hmm?
بيرسون
You can come. You can print it. It's better to print it. But again, use the template. For example, I tell students to use the Georgia Tech template CV. My university. They have CVs that are good for the market. If you use AI, it gives you PDF. We're late. We need additional lectures. Maybe we need 2 or 3 online lectures. Okay?
قبل الميجر.
No, after. For the material of the final. For the material of the major, I think we will have enough. Induction and DC. And for the induction, it will be from the examples after V over F. Most likely V over F control. And I will try to make the major 1 hour. Do you want it to be 1 hour?
حسب الاسئله
Less questions.
Why not?
بس كويشنز دكتور يعني غلطنا بسؤال واحد راح درجات كثير.
صح
اسئله اكثر افضل.
We'll see. I'm making it easy for you.
الوقت ما هو مشكلة صراحة يعني أتوقع أغلب الطلاب
No, if I give you two problems وخلاص. 2 long written problems وخلاص.
والله في خطوه
You solve the 2 problems and go. No MCQ, no.
نشوف ان شاء الله نشوف
شو ما في كونسبت.
Well, if I'm gonna make it 1 hour, 2 problems, it's better. يعني كان 2 quizzes. But the problem is that it has to be 20%.
كذا كويس.
Let me think, okay? Let me know next lecture, what do you want? Or we can make it 1.5 hours and then 1 additional problem for concept. Concept, I'm gonna make it a list. No MCQ. I don't think I'll have MCQ.
أحسن
لا ما نبي
No, list. What are the advantages? What is slip? Talk about.
شوف بعدين شوف معك
Okay. So last time, what did we talk about? We talked about the DC machines, صح? What did I tell you about the DC machine? The slip rings, anything before the slip ring is DC. What's after the slip ring? It's virtual AC. Why it's virtual AC? Because the rotor rotates. When the rotor rotates, the induced EMF becomes AC. We talked about the equivalent circuit. This is for separately excited, separate circuit. We talked about going from 360 to 462. We did Laplace transform and we developed some transfer functions for the speed omega and for the current IA. We take 3 and 4, we put them in the project block diagram. This is the project block diagram. Keep in mind, in the project, we have a different model for the mechanical. For the project, we have 1 over J times S. We do not have B, we do not have tau M. We just have 1 over J times S. Get it? That's the moment of inertia. We don't have friction. We don't have tau m. What is tau m? J over b. But because b is 0, the friction constant is 0, we cannot divide by 0. Clear? So you only have a j. Okay? Or you can say it's b plus j, no, it's b plus js and b is 0. Okay? Like that. In the project it will be b is 0, so it will be 1 over js. If you take the common factor, you have to make sure it's non-zero. Okay? Clear? So you have to put this block. These two gains are the same. It's called Km. What is Km? What is Km? It is EA over omega, or it is KFIF, which is K flux, K times flux. It's a constant number. Put it as it is. Okay? Now, from this, would this be a triangle in the project? This will be a triangle, this will be a triangle, this will be a transfer function, this will be a transfer function. There is a box called transfer functions, meaning. Did you ever do it?
Yes.
Okay. Now, if you do the math, you have different cases. I'm not going to focus on it too much. But sometimes you have b is 0. This is like our model, 1 over sj, our project. And this is the transfer function. But we are not going to have this transfer function. We're going to have every block separate. These, if you combine omega over v, this is the total transfer function. Now, some students, they don't want to do the project. They do one block of this and they are good to go. Okay? Now, what will happen if you disconnect the supply? There is no current. The speed will decay until 0. This is one of the theoretical questions. If the supply is disconnected, omega t will decrease exponentially. Clear? Now, we talked about the power flow. We talked about the equivalent circuit. And what did we say here? We say this is from EE360. If you substitute the equation, the torque and E, omega is Vt over Ka flux minus Ra over Ka flux squared times T. So it is a straight line that has a slope of Ra over K times the flux squared. So your initial speed at 0 torque is the fastest. This is the no load. Full load, depending on the load, where is the rated torque? If you want to control the speed, you either change the supply, or you add series resistance, or you change the flux. 3 methods. These are the conventional or traditional methods to control DC machines. For the series motor, because series motor has the field resistance RA and RA, and then it has a windings. Why do we have windings? For transient. For the transient. Here we are not doing transient now. We are looking at speed control in general. From steady state, you go through transient. If you want to study the transient, use Simulink. You go back to steady state. So the speed is like this. If it increases, while it increases, it's transient. Once it settles, it's steady state. So steady state, you can solve it by speed control, EE360. The transient, you solve it by solvers. You cannot do it by hand. Okay? So look at the series motor. This is the equivalent circuit of a series motor. What will happen if you do the same trick and write omega as function of voltages and currents? It will be Vt over K times the current Ia. Note that Ia will change depending on the loading condition for the series motor. So what will happen here, if you add more resistance, if you increase the resistance, what will happen? Omega will be less because we have minus. So الارو هذا ايش معناته؟ Increase the resistance. This is variable resistance. If you increase it, the curve of the speed goes down because you have a subtraction here. Clear? This is only for the series. So what do we learn? Controlling series motor is different than controlling shunt and separately excited. For shunt and separately excited, the equation is this one. You have to put it in the formula sheet. Where's the formula sheet? It's outside. Tell him to put it in the formula sheet. This is important. Also, the series has a different one. It is Vt over K times omega minus the summation of R's over the constant. So to control it, you either control the V or the R. But if you change V and R, you're going to also change the current IA. So it is interconnected. So a high torque is obtained at low speed and low torque is obtained at a very high speed. Series motors used for large starting torques. They are used in subway cars, automobile starters, hoists, cranes, mixers, maybe old elevators, but they are not as common as induction. So I think the oil pump is going to be induction because it's more reliable. That's my guess. So any question about the series motor control? So how to control it? Using these curves of series resistances. We're talking about non-power electronics. No choppers, no VSI, variable drives. This is just pure resistance, voltage, and field control. Is this used nowadays? No. So speed regulation. What is the speed regulation? For the DC machine, speed regulation is speed at no load minus your current load. Your load is your torque. It might change. So if you have a torque that is here, speed regulation is omega no load minus omega at full load over omega at full load. If you want to calculate omega and L, you can use this equation, I no load RA Vt over Ka times the flux. Or if you ignore I no load, usually if you ignore rotational losses, you can ignore I and L. It's very small voltage drop. I and L times RA is very small. You can simplify it to this equation, EA over Ka times the flux, which is roughly equal to the terminal voltage over Ka times the flux. This slide is redundant. Now let's talk about the first approach, adding resistance. If you add a resistance, armature circuit, it's called rheostat. Rheostat is the variable resistance that if you tune it, you can control. Instead of adding series resistance, you already supply the motor with a variable resistor, and then you change it until you reach the speed that you want. So this is the equation of omega. So this method is simple, and it's only used for short circuit. What is the drawback? This is one of the questions that I like to ask in the exam. The main disadvantage of this method is armature losses are substantially increased. So this is the curve. RA at 0 is that. If you keep increasing it, you might reach a point where the speed is too low, and then the losses are very high. I square R is going to be very high. You're going to have a voltage drop. Also, you're limited by until the speed is 0. You want to maintain that the speed is enough to drive the torque. Okay? Clear? It's not interesting as the induction. Terminal voltage. What will happen with the terminal voltage? In this method of speed control, the field current is kept constant. Armature voltage is varied. So if you increase the voltage, what will happen to the speed? Increase. So always look at these figures. If you increase the voltage, what will happen? It will increase. For a constant load torque, such as applied elevator hoist, this is, if you have a constant torque load, it means your torque is fixed, constant. إيش معنى constant torque? This is your load. If your T load is constant, then the intersection is the operating point. For a constant load torque, such as the hoist or the elevator, the speed will change linearly. If you increase the voltage linearly, the speed will change. For omega L squared, that looks like that, it's different. This is omega square. TL is the Zale project, proportional للفان. It's not linear. The curve is different. You see the difference? This is non-constant. It's not linear. The speed will increase more linear, same as the path of the load. Always your speed is where your load intersects. زي نفس induction. In an actual application, when speed changed by changing the terminal voltage, the armature current is kept constant. So usually, the armature current, we control it. We control the field circuit. The field circuit here, we always make sure to maintain constant field. We do not vary them twice, okay? How we do it, there's controllers in place. If it's separately excited, there is a controller there for the field control. I think the project, maybe it has some field control, but we'll see. So why it's good? Because it provides smooth variation of speed from 0 to the base speed, easily controlled by solid state drives. So you can implement power electronics to change the voltage. Constant current and torque are easily achieved. So here we have another speed. Here we have constant torque. Here we have omega. This is another curve. I don't think it's important. However, this is the intersection where you have the control. Okay? The last type of traditional control is the field. So what are the methods? Resistance, voltage, field. In this method, the speed is controlled by varying IF. This is usually achieved by changing RF control. So they have another resistance, they change it because here you apply terminal voltage, the same voltage. The only way to change IF is to change the RF. If magnetic linearity is assumed, the flux will be proportional. So we assume, do you remember the flux IF curve? We operate near the knee. So this is the linear region. If you increase the flux, if you increase IF, the field, the flux will change linearly. We do not have saturation. This is what's meant by this statement. Magnetic linearity is assumed. We operate up until the knee. Therefore, Ki times flux equal Kf times If. Substitute with If and then you have speed curve. What will happen if you increase IF? Osama, what will happen? If you increase IF, speed will decrease. Why? Because the subtraction has the square. Akbar. It's Vt over, if you make IF bigger, it will be small, minus. Yes, so the speed will be smaller. Here we start RFC0. If you increase the resistance, you increase IF. You decrease IF. إذا زودت المقاومة يقل IF. معناته أن اتجاه IF يزداد حسب السهم هذا IF. Resistance increase this way. The biggest resistance, the max, gives you the minimum IF.
Okay.
The smallest resistance, RFC, is 0. You already have a fixed RF here. If you add them together, then the field current
Max.
IF4 is the max, and it gives you the minimum speed. So if you do the locus of the resistance, you notice that you start with RFC 0. If you increase it, you're going to have larger omega, smaller IF. So this is locus control of changing the RFC. This is the locus control of IFC. I'm not going to ask you numerical questions, but try to understand. Clear? أحمد, is it clear?
كيف؟
Clear, واضح الكيرف هذا, it maps the information here.
أي.
It makes more sense. If you increase RFC, if you increase it to the max, you're gonna have small IF and more speed. If you increase RFC, you're gonna have smaller IF and bigger speed. What is the optimal way of controlling the machine? Do you remember V over F control? We increase V over F, keep increasing V until we reach V rated. Once we reach V rated, we stop. We only increase the frequency and we go to the flux weakening, the field weakening. You remember this in V over F? You cannot exceed V rated. Same story here. What will happen if you go to V rated? You're gonna have omega rated, omega based. You cannot exceed voltage. Never ever apply larger voltage in your machine. It's not a smart idea. Then after that you have the IF control. So what do we understand from this curve? What we understand from this curve, adding series resistance is not good as a general control strategy, it's only temporary. But V and IF control traditionally are the one used. You start with V control until you reach V rated. Once you reach V rated, you do IF control after the omega base to increase the speed. So to reduce the speed among the rated speed, you use V control. To increase it, use IF control. Here the torque is constant. After the IF control, you have to drop the torque. You cannot supply enough torque. Why? Because you're going to increase the field. If you're going to increase IF, you're going to increase IA. If you increase IA, you're going to increase the basically you have to maintain constant power. So if you increase the speed, you have to decrease the torque to maintain the same power. Why? Because power is limited by VT IT. So if you keep increasing IT, you have to maintain the same power. You cannot overpower the machine. You can't. Conservation of memory. If you increase the torque, your torque will be decreased because IF increases. So this is what we call the constant power. So speed control from 0 to base speed is usually achieved by armature voltage control, BT. Speed control beyond the base speed is obtained by decreasing the field current. You decrease the field current. What will happen if you decrease the field current? Here, decrease the field current. What will happen if you decrease the field current? Increase the speed. What will happen if you increase the field current? Decrease the speed. So now, if you want to increase omega, you have to drop the torque to maintain the same power. Because power is limited by VT/IT. It's fixed, constant power. So if you decrease IF, you're gonna increase the speed and reduce the torque. This is called what we call it field weakening. Field weakening. Same as V over F control. Do you remember? After the voltage increase, what will happen to the frequency? You increase the frequency and then because your flux drops. At the base speed, the armature terminal voltage is at rated value. If armature current is not to exceed the rated value, heating limit, speed control beyond base speed is restricted to constant power known as the constant power operation, also known as field weakening. So, field weakening and constant power, YouTube, field weakening and constant power, they are the same names, so two names are used. Okay? This is only the traditional approach of controlling the machine. Let's do a quick example, a review example. So you see this example, we'll solve it This is not required, okay? Why it is not required? Because you're gonna already do the project. So if you want to solve it, you can solve it, but it asks you to develop the transfer function, compute steady state, so it asks you to solve the differential equation. I'm not gonna ask you to do this in the test. It's for your own knowledge. It's beyond the scope of this course, but here is some example if you want to see questions, if you want to do, why do I put this example? If Nawaf wants to do a master's degree in electrical engineering, you have to do it. And you do. You take a course that will ask you to do it. Okay? If you want to do it. But most of you who are doing the simulation project, then solve the steady state using the simulator. So why would I ask you to solve differential equation if you can solve it using MATLAB? Because he asks you how long does it take the motor to reach 0.95 of the speed and find the value of the B constant of that machine. So you can solve it, but this is not required. What's required is these examples. So let's start with the example from EE360. So at 250 volts, I forgot to mention this is an input power, okay? Write it down in your notes. You have to watch the YouTube before the exam. You cannot skip the YouTube lecture.
Input power, input voltage.
No, this is input power. While solving this test. Usually it's output power, but in this example it's input power, okay?
هذه 250 واط ولا 250 واط؟
Oh, no. My bad. So the motor absorbs input power of 25 kilowatt. This is input power. So this is input power, 25 kilowatts. Okay? So 250 volt shunt motor has armature resistance of 0.25, field resistance of 125. In EE360 you can draw this circuit. Here they're adding this inductor for transient. This is also a correct circuit. This is 250. So this is RF, this is RA. And is it a motor or generator? Motor. So the power comes from the supply. So draw the equivalent circuit. This is a 360 equivalent circuit. Calculate the motor constant. So to calculate the motor constant, you start with IF. What is IF? IF is here, 250 over RF, which is going to be 250 over 125. It's 2 amps. Then what is the armature current? He's telling you at no load, motor current is 12 amps, so that's I terminal. So minus 2 amps, the armature is 10 amps. So what is EA? Is 250 minus IARA, which is 247. What is the no load speed? It's 2 pi over 60. This 2 pi 60 for RPM. 60 has nothing to do with 60 hertz. You remember this equation? This is from physics. Omega is 2 pi over 60 N. This is for any speed, any machine. It's for synchronous machine, induction machine, DC, stepper motor, universal motor, etc. And also it's used in physics 102. Remember physics 102? To convert from revolution per minute to radians per second. So this 60 has to do with conversion from minutes to seconds. So what is the no load speed? Is 1000 RPM converted to 104.72. So how to get the constant? To get the constant, you have to go back to the original equations. And it is this equation, original equation, the first slide, before the transfer function. So it is here. EA over omega. So 247 over 104. So what is the motor constant in example 1? What is it? This is, example 1 is solved example 1. It's going to be 1.187. Oh, I forgot to mention. He used this equation, Ka times If times omega. Either is fine. You can get this Ka, or you can get Ka times 2. Both constants are the same. If you find this is a small, you remember K is Kf times If. So either you calculate this K or you calculate this K. It's the same. Both are motor constants. Because the field current is the same. So it's either this or 2 times that. Both are acceptable answers. Clear? Now okay, time is up. We will start from here next lecture.